Hello, so this is Edexcel Year 1 Maths, Pearson Textbook, Chapter 14, Section 14.3 Exponential Models. So this is just to take you through and explain the maths involved and also the example. So this is about exponential models, and with these questions I generally find students are put off by the words. The actual questions are usually quite accessible, but it's the words that put people off because it's in a problem context. And the context may be a scientific context and you don't like that area of science. It may be an engineering context and you go, oh, I'm not really keen on engineering, so then you think you can't do it. And it's really important to understand what the questions ask mathematically and not be put off by the context of the question, because that's generally where I feel things go wrong. So let's pause and read what it's saying. The density of a pesticide in a given section of field, P milligrams per metre squared, can be modelled by the equation P equals 160 e to the negative 0.0 or 0.006 t, where t is the time in days since the pesticide was first applied. Use the model to estimate the density of the pesticide after 15 days. Make sure to start with that you're clear what that actually says, and then let's go through and pick out some key parts. So, first key part is this. This is our function. Oh, perhaps a bit too thick there. Let's just draw with a thinner line. And this is the function that describes our model. So I'm going to write that P equals 160 e to the negative 0.006 t. And P is density. T is the time in days. That's quite important because as these questions get more difficult, they'll say it's the time in days and then they will ask you for a month and tell you, I mean, that's quite hard because it's got 28 days, 30 days, 31 days, or even 29. But they will write it in a different unit. And what I find people do is they don't check which unit are we working in. So remember that T is in days. That's really important. And part A says use this model to estimate the density of the pesticide after 15 days. So actually, part A looks quite simple because for A, T is equal to 15. So I can just substitute 15 into this here instead of T, because remember T is measured in days, and I type that in my calculator. So off you go, type it in your calculator. What do you get? Well, I'm hoping that you managed to get 146.2. Now don't forget your units because it's density. You're given the units up here, remember, so make sure you pick them up and use them, and that's milligrams per metre squared. So actually, part A, after all of those words, if you think of what it was asking, it was asking you to do substitution, which you're brilliant at that, so that's easy marks. Fantastic. Next thing, it's quite common this question comes up, and not just in this format, comes up in other formats as well, in other questions. And here it says interpret the meaning of the value 160 in the model. And if you're looking, that's that bit there in your model. And sometimes this is where people get a bit stuck. Well, this is all your awareness of what an exponential graph would be. And that links to your knowledge that came before. So I'm going to just draw a quick exponential graph down here. And this is a negative exponential graph, so immediately I know that I'm looking at a graph that's going to go like this. Okay? Can you remember what that point there is? Well, that's the point when, and for this graph, remember this would be T, and this would be P. And that point there, where it intersects the p-axis, is when t is 0. So if we look at this for part B, and this bit here, remember we're looking at this here. T is going to be 0, so it's 0 lots of that, so it would be e to the power of 0, which anything to the power of 0 is 1, so p equals 160. And you should be, and you really need to have that knowledge in your head that the significance of this is when this here, the exponent, is equal to 0, then e to the exponent is 1, and this p, the density, will take on this value. So let me just go through that again. That value, 160, that is multiplying the exponential, it will be the density when the exponential function is 0. So that's when the exponent, which is this part up here, is 0. So here we can see p equals 160. If we go back to answer the question, interpret the meaning of this value of 160 in the model. It means that when t equals 0, so at the start, p equals 160, don't forget those units, milligrams per metre squared. And I would even write here at the start, because that's quite important. Because if we go back to the question, the density of the pesticide at the start is 160. Now, there's other ways they could ask that question. They could say, what is the value of the density of the pesticide at the start? So that's exactly the same question as interpret the meaning of the value of 160. It's what the density is of the insecticide at t equals 0. So be aware, same question, multiple ways of writing it. And it's clearly understanding what the effect of that multiplier is on the exponent. So we can now move on to part C. So part C says show that dp by dt, so differentiating density with respect to time, is equal to kp. So I'm going to move down, or actually I might move across for part C over here. And for part C, and I think I'll pick a different colour. So C, I know that my function, I'm just going to write my function out again because I like things to be clear. And I'm asked to find what dp by dt is. Now, it's very easy to get caught up in it saying, show that it equals kp. Well, the first stage is to find out what dp by dt is. That it equals kp at the moment, and k is a constant, and state the value of k, I can get stuck looking at that, whereas actually the key part of this is, first of all, get on and differentiate it. So this requires you to remember how to differentiate an exponential function. If you can't remember, you'll need to look back at my previous video. Hopefully you remember it would be negative 0.06. which is the differential of the exponent, the differential of that bit, multiplied by 160 e to the negative 0 point, or 0, better still, 0.006t. Now, if you remember, or if you can look back just above, what you will notice is that there is p, because that's what you have been given in the question, that p is equal to, and equally this bit here is also p. So actually, if I think about what they want the answer in the format is, it's equal to kp, then I can see from above it's negative 0.006 multiplied by p, because I can see that when I compare this and this, dp by dt is negative 0.006 multiplied by p, which is what I've written here. Now, if I now compare these two, what's my value of k? Well, k is equal to negative 0.006. So k is just the differential of the exponent. And that answers, I believe, part C. Let's just go back and check, because it's always worth checking we've answered the question correctly. C, show that dp by dt equals kp, where k is a constant, and state the value of k. So I've shown that clearly here, and I've then written down my value of k. Now notice all my workings so that I am showing what I'm doing clearly. Must make sure you share your method clearly to gain all the marks for showing understanding. D, interpret the significance of the sign of your answer. So I'm interested in the sign, that's the bit that's important, of your answer in part C. So if I go to part C, I am multiplying my p value, which is here, by a negative number. So my gradient is negative. So key thing here, gradient is negative. What does that tell me? And the reason I'm talking about gradient, remember, is because this is a differential, and the differential of my function would be its gradient. So, what does this mean, as we said? We're saying that if its gradient is decreasing, the density of the pesticide is decreasing. And that's significant for a farmer. So if I'm going to slightly alter this question, I could actually ask, what is the significance of the farmer? Well, the significance of the farmer is that the quantity of pesticide is decreasing, so he's more susceptible to pests. And then I could go on and give you some advice about at what point you needed to actually spray some more pesticide. And this is actually real maths. This is maths that's applied, and it's something that showing you how to take your maths and actually use it in a model. So that's part D done, because it just said interpret the significance of the sign. The gradient is negative and the density of the pesticide is decreasing. E now. E says sketch the graph of P against T. Now, what you'll notice is I've already done that because I just love a graph. And I'm just going to redraw the graph because there are some problems with the one I've drawn above. First of all, time. Time can't be negative, but at the time I was sketching that, I was actually talking about what an exponential function is that's a negative, has a negative exponent. Remember, that's the same as a fractional exponent, so a fraction where that fraction is less than 1. So here I'm going to draw on, but I'm going to start at 0, and here's my graph, just keeps going. Notice it never reaches 0 on that axis because it's an asymptote, and we talked about that in the last diagram, so it's important that you go back and remember that, and that value there is 160, and that would be your graph. So looking back at that question, mathematically, all within your capability. But it's the words, as I said, that puts people off. So when you see one of these questions, they want to really go for, because if you can practice that interpretation of the question, you can fly through these. And really, this is real maths. This is applied maths. This is using your maths rather than just being asked to differentiate it. It's actually a reason for doing that maths, which is what maths is all about, using it. Okay, off you go, do some practice.